All right. So carbon-13, if you think about organic molecules that have carbon and hydrogen, well, hydrogen-1 is by far the most abundant isotope of hydrogen. It's like more than 99% hydrogen-1. And so this is why it's so easy to run a proton NMR spectrum, because most of the protons are hydrogen-1. So you pick that up very easily. Whereas carbon-12 has an even number of protons and neutrons. And so you can't run a spectrum on carbon-12. You have to run it on carbon-13, which has an odd number of neutrons. And so carbon-13, if you remember from this class, the carbon-13 only makes up about 1% of the isotopes of carbon, whereas carbon-12 is about 99%, and then there's a tiny, tiny bit of carbon-14. So we only have about 1% of our sample containing any carbon-13. So you actually need a more concentrated sample, and you have to use a more sensitive receiver coil, which is basically you got to have a more sensitive instrument, okay, in order to pick it up. But the bottom line, I mean, to me, is that you need more sample. It's got to be more concentrated. So let's say you only have a few milligrams of a sample. Oftentimes, carbon-13 samples are run overnight, so they can just keep pulsing the sample over and over and over and trying to average it out and get a good spectrum. But in proton, remember that chemical shift, the splitting or multiplicity, and integration were all important. Well, in carbon-13, it's a little simpler. All you have to worry about is chemical shift. There's no integration whatsoever. Now, notice that it doesn't say there's no splitting, because there are some experiments that you can do coupling to protons, and I'll mention that briefly, just very quickly. So in a carbon-13, the proton carbon-13 splitting, there is proton carbon-13 splitting. However, what happens is that it's really complex, that it basically a lot of the signals will overlap, and then it becomes unreadable. So it's not really useful. That's the problem, okay? Again, you do get splitting, but it's not really useful to read it. It's really hard to read it, as a matter of fact. And so in order to get a clear carbon-13 spectrum, we do what's called a decoupled spectrum, which basically decouples all the protons from the carbon nuclei, and that way we just get a bunch of singlets. Okay, so every unique carbon is going to produce a singlet. Of course, if you have two carbons that are chemically equivalent, they're going to overlap and have the same chemical shift. So now, with respect to the frequency of radio waves that are required to excite the sample or to cause the nuclei, the carbon-13 nuclei, to come into resonance, it's a larger range or a broader range of frequencies. So instead of using the typical 0 to 12 ppm that we do for proton, carbon-13 signals are going to appear between 0 and 220 parts per million. So it's a much bigger or a wider range of frequencies. And each signal in the carbon-13 is, like I just said, is going to represent a unique type of carbon. So just like protons, where it's not every proton that's going to give you a signal, it's every unique proton that's going to give you a signal. Same thing in the carbon. Not every carbon is going to give you a signal. Every unique carbon is going to give you a signal. And so we have to take planes of symmetry and axes of symmetry into account when we're determining how many carbons are going to give signals in a carbon-13 NMR spectrum. So let's take a look at these three molecules here. Yes, we talked about these same three molecules earlier today with respect to the number of proton signals we would see. But if you look at this compound here, this is called metaxylene. You see that there's an axis of rotation here. Okay, so these two carbons are chemically equivalent. These two carbons are chemically equivalent. These ones are chemically equivalent, and these ones are chemically equivalent. So in the carbon-13 NMR spectrum, we would only see 4 signals. If we look at the next compound, you can see that the same rationale. You see that these carbons are chemically equivalent, as are these ones, as are these ones, okay? Whereas the one that I'm putting in the black box, it's unique, and the one that I'm putting in the yellow box, it is unique. And so we have a total of 5 signals here. And then in this one here, when you have the two methyl groups para or on opposite sides, we have 2 axes of rotational symmetry, and therefore you only get 3 different signals here. So again, just like we could with proton NMR, we can use carbon-13 NMR to very quickly determine, different isomers like these three here. So basically very quick. Now, you're probably wondering, well, what are the chemical shifts of the carbons in a carbon-13 NMR spectrum? Well, if you took a look at the handout that you'll be provided for quiz 15, and it's the same one that you had for quiz 14, you see that there aren't very many different types of carbons with respect to chemical shifts. Okay, it's a little simpler. From 0 to 50 parts per million, those are all your sp3 hybridized carbons, like your methylenes, methyls, methynes. If you have an sp hybridized carbon or an sp3 hybridized carbon that's attached to an electron withdrawing element like nitrogen or oxygen, those fall in the range of 50 to 100 parts per million. If you have any sp2 hybridized carbons, they come out between 100 and 150 parts per million. And when you have a carbonyl carbon, those are going to be the most deshielded, right? Because you've got that strong electron withdrawing effect of the carbonyl group. So those are going to have the highest chemical shifts, around 150 to 220 parts per million. And that's really all you need to know for the chemical shifts of carbon-13. Now, I told you that we don't look at the splitting of carbon and proton, okay? Because I told you it can be very, very complex. There are exceptions where you can use a technique called off-resonance decoupling that allows you to get some of the information. So I'm going to go back here and in 15.11 is where it was, okay? And say there is something called off-resonance decoupling. I'll write it down here. Off-resonance decoupling, okay? And in that, they run these experiments where you can get some carbon-proton coupling that you can decipher, I guess, for lack of a better word. So if you have a methyl group, it's going to appear as a quartet. It's kind of like the N+1 rule. If you have a methylene, okay, CH2, it's going to appear as a triplet. If you have a methyne, it's going to appear as a doublet. Okay, and if you have a quaternary carbon, meaning it's attached to no hydrogens, it's going to appear as a singlet. Okay, now the reason why it's not in my slides is I just didn't put it in there, but it is in our book. And the reason I bring it up is because if you look at ACS study materials, so ACS study guide, or if you look at some of those MCAT or DAT materials, sometimes they will show you spectra where they do off-resonance decoupling. So I just wanted to mention it to you that it is used from time to time. Now, the last section of this deals with what's called DEPT carbon-13 NMR spectroscopy. DEPT, D-E-P-T, stands for distortionless enhancement by polarization transfer. And this is just a couple of special experiments that you can run. Now, you don't need to know any of the theory behind it. The textbook goes into a little bit of detail about it. All you need to know is what's summarized right here. There's two experiments. There's one called ADEPT 90, and there's another one called ADEPT 135. When you run ADEPT 90, the only thing that shows up in the spectrum are methine protons, nothing else. Like what? Nothing. Nope, nothing else shows up in the spectrum. Whereas if you run what's called a DEPT 135 experiment, again, you don't need to know the theory of it. If you have a methyl or a methine, they show up as positive signals. What does that mean? That means they're going to be pointing up, okay? Whereas if you have a methylene, they're going to be pointing down. Now, what's the significance of all this? Because if you run a regular carbon-13 spectrum, just our regular decoupled spectrum, then you run a DEPT 90, and then you run a DEPT 135. Well, the good news is you would be able to distinguish between all four types of carbons, whether it's a methyl, a methylene, a methine, or a carbon that has no hydrogens. Let me prove it to you right here in this table. Here are all the signal patterns. So again, I told you, if you just run a regular carbon-13 spectrum, okay, it's going to show you all the signals for every unique type of proton or to carbon. But if you run a DEPT 90, all you see are the methynes. So now you can go back here and you can tell which ones were the methynes from the get-go. Then if you run the DEPT 135, it tells you, well, the positive peaks are methyls and methynes. So anything that you identified as a methine, or sorry, anything that's pointing up that you didn't identify as a methine, you know it's a methyl. Anything that's pointing down, you know that's a methylene. And anything that doesn't show up at all, well, that you know is a quaternary carbon. And so you're able to go back to your broadband decoupled, your initial carbon-13, and you're able to identify all the different types of carbons, which is pretty cool when you think about it. So this is what a carbon NMR looks like. You see you have the proton NMR above. Now here they're not showing 0 to 7 parts per million. They're only going up to 4. But the carbon can go all the way up to 220 parts per million. But here they're just zooming in on the important part. So you see how in the carbon-13 NMR, so this is a carbon-13 NMR, all you see are singlets, right? There's 3 of them here. There's 3 of them here. So you see that we have a total of 1, 2, 3, 4, 5, 6 different types of carbons in this compound. I'll show you another example of a carbon-13. Okay, here's another carbon-13. Again, it can go all the way to 0 ppm, all the way up to 220, okay, parts per million. They're just zooming in on the parts that are most relevant. But you can see you have a total of 1, 2, zoom in here, you got 3, 4, 5, 6, 7 unique types of carbons. Now, I'm going to say one more thing before I stop recording this video, before we tackle some problems, is that they told you in the book that there's no integration in carbon-13. And there isn't, okay? There's no integration reported in carbon-13. All these numbers that you're seeing, these are just chemical shifts. 179.9 parts per million, 140.4 parts per million, etc. But there is one thing that's kind of interesting here. You notice there's a big difference in the peak height here for these two. Okay, these two peaks are much higher. Now, you can't take this to the bank and cash it in 100% of the time, but most of the time, or a lot of the time, I should say, when you have peaks that are like double the height of most of the other, peaks, what that usually means is that it's going to be twice the number of carbons. So let's say this was 1 carbon, this was 1 carbon. These two here are probably both representing 2 carbons, 1, 1, like that, okay? Not 100% of the time, but a lot of the time. When the peak is really giant, it's probably representing more than 1 carbon.